Okay, so let's get started. Welcome to the final and thus closest to Popple time-wise session of VMCAI. We'll have 4 talks and the closing, including the announcement of Best Paper Award. And our first talk is software model checking for programs with dynamic thread management, also called Petrification. And the talk will be given by Frank Schüssele.
Yes, thank you for the nice introduction. So our contribution is to develop a practical verification algorithm for programs with dynamic thread management. So to get started, we first need to get to know what exactly is dynamic thread management. So dynamic thread management is motivated by C. There in the pthread library or POSIX thread library is one way to create, to write concurrent programs. There's also a similar concept is also used in other programming languages, for example, like Java and also others I'm not too familiar with. The key features are that there is a fork in the pthread library. It's called pthread create, which can be used to create a new thread dynamically. And there's a join statement in pthread library. It is called pthread join to destroy an existing thread. So these are just usual statements in this programming language, and they depend on the control flow and data flow, because maybe the fork or join, it might occur inside of a loop or inside of an if, and thus it may depend on the evaluation of some program variables or some expression. And now let's take a look at an example for dynamic thread management. We have 2 thread templates here. One is the main thread that is initially active, and on the right hand side there's a worker thread which is blank for now. We will take a closer look to that in a second, but for now just let's take a look at the main thread. So we have some statements there where we initialize variables or some if and some while, and inside the while you can see there's a fork statement. So it really has the syntax that as the first argument you have some expression that is the thread ID of this thread, and as the second argument you have the name of a thread template. So what this means here is inside the while loop we create a new instance of the worker thread. And as you can see, it happens here inside of a loop, and this loop is just a non-terminating loop, which means we create infinitely many instances of this worker thread, assuming here that there are unbounded integers. And this worker thread is identified by the first argument. So what this means here is that every instance of the thread is identified by the number of iteration it was created on, because the I is here used to count the number of iterations. And also you can see there's a join. It even happens inside of an if, so it really depends on the control flow and data flow, which means here this join is not executed in the very first iteration, only afterwards. And what this does is it destroys an existing thread that matches this thread ID. So here we join the thread with ID I-1. This means that we just destroy the thread that was created the iteration before. So, and this means that although there are infinitely many instances of the thread, at most 2 of them are active at each time, because we create one instance, and the next iteration we create one again, but then we destroy the one from before, and so on and so on. But now let's take a closer look at the worker thread. So here the worker thread is rather simple. It first increments this global variable c by I, then asserts that it still satisfies some bound using an assertion, and afterwards decrements c by I again. And now we ask whether this program is correct, which means does it always satisfy its assertion. And this program is indeed correct, but it's not as obvious because it's really complicated, this thread creation and destruction and so on. So we want to develop a verification algorithm to check this for us. But first, I want to introduce the concept of the thread width. The thread width is simply the number of instances of a thread template at any point in time in any execution. So consider our example again. We have seen that there are infinitely many thread instances at each point of time. However, only a finite number of them are active at the same time. So this means the example just had a thread width 2. Now I want to present our verification algorithm. So first we start to model the program by with a fixed number of thread copies n. Usually we start with n equals 1, but this can be changed. And we represent the control flow of this program using Petri nets, and thus the name Petrification. So then we have such a representation of the program with only a fixed number of thread copies. Then we apply an existing verification algorithm to such a Petri net, and this, depending on the output of this this verification result, we may start over again, which means if n is less than the thread width, which means that there are more than n threads active at some point in time, then we increase n and repeat over. So we then model the program with a larger number of thread copies. Now let's reconsider our example again. On the right-hand side, you can see the example. On the left-hand side, you can see the petrified version of the program. So the Petri net representing the program with one thread copy. So there are several places here, and some of them are simply used, those without labels, to track, to represent the program locations, and others like not in use, and insuf are used to track the active threads. So we also call them thread monitor places. And also on the very top, you can see there's an error location. So therefore, since it is an error location, it is labeled as an accepting place in the Petri net. And also, you can see I split some by colors there. So on the very top, there's a thread copy of the worker thread. On the bottom, there's the main thread in red. And yes, and you can see that there are tokens in the places. So initially, only the main thread is active, so it has a token in its initial location, and the worker thread is not active, so there's a token in its not in use place, so it is not used yet. It was not forked yet. And yes, there are obviously also transitions connecting the places, so many of these transitions are simply used to represent the control flow inside the threads. For example, the transition on the very left simply initialize the variables and shift the token one to the next location of the main thread. However, there are also some, okay, the same also applies for the other control flow features like loops and if. But then the question is, how do we model the fork and join in this Petri net? You can see the fork is, so one instance of the fork is modeled here. So we simply say, okay, if we are in the given location of the main thread and this thread is not used, then it is used afterwards. And to track that we have the correct instance, we also introduce some thread ID variable and assign the I here that we can see from the join. For the fork, we assign this I to the ID variable. And this the join also makes use of this ID variable, and it simply checks, is this the correct thread to be joined? And then it terminates the thread. So it was in use before, this no more used afterwards. And there's, however, a second transition derived from the fork. This is this here, labeled with true, so we can always take it. What this says is, okay, we have only one thread copy, and if this thread copy is already in use, and we try to fork another thread copy, okay, then we know our modeling was not sufficient, because there is only one thread copy, and we want to create two thread instances. Therefore, we label this also as an error location, as an accepting location. Now, let's show a run in this Petri net. So, okay, so first we execute the very first statement, an initialization of global variables in the main thread. Thus, we shift the token to the next place and fire the transition. Then we execute the fork, so the fork on the top. Then we shift the token from not in use to in use, add an additional token to the initial location of the worker thread, and also continue in the main thread. Okay, then we do two more transitions in the main thread. So the if condition is not satisfied, so we skip over it and do not a join. Then we increment I and start over with the loop again. However, then we can execute another fork. But our only thread copy is already used. Then we can can fire only this insufficient, this transition to the insufficient place, and thus reach an error place. So this means one thread instance, one thread copy was not sufficient to model program. What we do then is we introduce another thread copy. It looks really similar. Now we have on the very bottom another thread copy for the worker thread. And now we apply our verification algorithm again. I won't go into detail. However, the verification algorithm for Petri nets then concludes that this Petri net program is indeed correct. And thus, the program on the right is also correct. Okay, now let's get to some challenges of this algorithm. So for the fork, we need to ensure that no active copy of the thread template is reused, because there only, only one copy can be used at the same time. And for the join, we need to ensure that the matching instance of the thread copy is destroyed, and this depends on the evaluation of the thread ID. Okay, now let's take a look at the implementation. This was implemented in the Ultimate tools, GemCutter, Automizer, and Taipan to verify C programs that use the POSIX thread, so can really model the pthread create and pthread join by fork and join, seen in our example. And these tools are the top 3 tools in the VMCAI 2024 concurrency safety category. Okay, now it's time to conclude my talk. So our contribution was that we have a practical verification algorithm for programs with dynamic thread management. It has proven to be successful in VMCAI, and this algorithm has some nice property. It is complete for programs with a finite thread width. So if there are only a finite number of threads active at each point of time, we can actually verify this program. There's, however, some small side note This only is true if the underlying verification algorithm that verifies our PetriNet program terminates. So that's it. Thank you for your attention, and I'm happy to answer any of your questions.
Time for questions?
Did you consider using colored PetriNets, since you seem to have many copies of the same subnets?
I'm not too familiar with colored PetriNets. Something I did not mention is we have a verification algorithm for PetriNets, but only for one safe PetriNets, which means in every place, at most one token can be.
One safe.
Yes.
Okay. And if I may, a second question.
Sure.
Will you consider adding timing constraints? Would it be useful? For time PetriNets.
I have not thought about that. We use this mainly to model C programs and without any timing. Yes?
Does your tool model data races?
It's not right. We have, okay, let's go back. We have this verification algorithm, and we apply it to a program that looks something like this. It just has, it checks for assertions. So this tool does ignore that. However, what we do is we translate a C program to a program which looks something like that. And in this modeling, we can also model data race and check for data races.
Thanks. I actually had one question about what you mentioned about the restriction of the underlying PetriNet model checking algorithms.
Yep.
What consequences does this have for the problems that you can check? So does it mean that in certain cases it will not manage to verify, or will it?
So what do you mean the property for this?
One safe. Do you always generate such PetriNets?
Yes, this algorithm always generates such PetriNets.
Any other questions?
You only check assert statements, so you do not consider liveness properties, just safety properties?
Yes, this is true. Okay. There is, however, some kind of ongoing work about that. I mean, the modeling itself could work similar. We need just a different acceptance criterion for this PetriNet program.
Okay, if there are no further questions, let's thank the speaker.